I have in mind now to do an example of the electric dipole moment using the electric dipole moment. And two things. First of all, remember that the dipole moment is defined as the product of, in a dipole, the product of the charge that is experiencing the torque and the total distance between the two charges that make up the dipole. Okay. That derivation and that definition depends on the assumption that the two objects in the construct have both the same magnitude of charge and also have the same mass. Pardon me. What I'm going to do for you now, and this is the second thing, is an example that's more complicated in that neither of those two assumptions are going to be true. Nevertheless, I can extend the concept of the electric dipole to be useful. The other thing about this example is, as I say, it is more mathematically complicated, and so this is for those of you who wish that once in a while I would do a problem that is sort of mathematically challenging. I do this occasionally. However, before I get in that, I don't want you to freak out about the math, and I don't want you to get lost in the math to the extent that you miss the essential concepts, which is that when you have an object, a molecule typically, that is polar, one side is more positive than and the other side is more negative, then this thing is going to experience a torque in an external field, and the result will be that the molecule will get rotated so that it tends to align itself or get aligned with the external electric field. This is very important in the biological sciences. Surely the most common polar molecule of all is water, and it is constantly getting rotated due to the external fields of the various atoms and molecules and things with which it interacts when it goes into and out of cells, transporting other ions with it, calcium ions and fluoride ions, and not fluoride, but calcium ions and sodium ions and chloride ions and so on. So very, very important concept in discussing how polar molecules, not just water, manage to transport their way through a cell wall. Okay, so I've written the problem up here for you, as you've probably already read it. So we have a hydroxide molecule. You remember hydroxide is it's an unstable thing, but that's all right. One oxygen and one hydrogen. So this is part of a water molecule, but this has an overall negative charge, but that's all right. It doesn't change our analysis here. It's in a uniform electric field. Surprisingly enough, this uniform electric field has the same magnitude as the one in the previous example, 4 times 10 to the minus 6 newtons per coulomb, and oddly enough is oriented at the same angle, 30 degrees or pi over 6 radians. So let's calculate the torque, the net torque that this thing experiences, and the angular acceleration that it gets from that torque. Oh, this is starting to ring lots of bells. Okay. Angular acceleration. All right, step 1, draw a diagram. Okay, we have a hydroxide, oxygen, hydrogen. Okay, so we have positive hydrogen there. We have a negative oxygen there, and they are separated by a distance d. Okay, and they are immersed in a uniform electric field at a relative angle of 30 degrees. So I guess I'll do it like this. I'll draw it like this for simplicity. And so There is our angle theta, 30 degrees. Oh, sorry, you can't really see it all that well. Okay, good. And there'll be forces and therefore torques. The force on our negative oxygen here is going to point in the opposite direction of the electric field at that point. And so this is the force on the oxygen. The force on the hydrogen will point that way, and it will be smaller than the force on the oxygen. Why? Because the charge on the hydrogen is smaller than the charge on the oxygen. Okay, so this will be F plus. And as a consequence, there will be torques, and our moment arms here. Now, we're going to have to be a little bit careful with the moment arms, and I'll get to that. But the moment arm for the hydrogen is pointing this direction, and so the moment arm is this way. The force is that way. So if I cross the moment arm into the positive charge, I get a torque that points out of the board. And the moment arm for the oxygen is going to point that way. And so our moment arm crossed into F, again, the torque points out of the board. It's not crucial that we know the direction of the torque, but, you know, why not? We're here. I guess I'll put it here. So the torque is pointing out of the board. Torque pointing out of the board there also. Okay, great. So this whole thing is going to get rotated to align, and we'll end up getting aligned with the external electric field. All right, there's our diagram. Step 2, impose a coordinate system. And let's see. Doesn't really matter. I'll choose a color usefully here, and I'll just do this one. X direction and Y direction. We're not going to desperately need the coordinates except to use them as a reference for measuring our angle. So that would be all right. So I suppose if I wanted to, well, yeah, I'll leave it at that. It's fine. X. Okay, and finally, solve the problem. Okay, I warn you again that the solution here is going to be a bit more complicated than what we saw in the very first example. Conceptually, it's no different. That is, what we're going to do is we're going to calculate the torque on the hydrogen, calculate the torque on the oxygen, add them together to get the total torque. That total torque will be related to the dipole moment crossed with the electric field. Okay. The problem is that we can't use just a simple formula that I derived earlier. We have to take it kind of slowly because the two particles don't have the same charge, nor do they have the same masses, and so that's going to have consequences. So let's take this by easy stages. As far as them not having the same masses, that means, as I suggested earlier, that the center of mass is going to be closer to the oxygen than it is to the hydrogen. And indeed, okay, I just made a mistake. I just made a mistake in my calculations in my example, so I'm going to pause the recording and correct that mistake, and I'll be right back. Okay, sorry about that. Okay, sorry about that. I hated to make that kind of mistake unnecessarily. Right. So as I was saying, I'm sorry. Since the oxygen has 16 times the mass, hopefully you remember that from chemistry, of the hydrogen, that means the center of mass of the system is going to be 16 times closer to the oxygen than it is to the hydrogen. Okay. Um, and for that matter, they don't have the same charge either, and so that fact is going to affect the dipole moment. So the charge on the oxygen, call that Q sub O, is negative, but we don't have to worry about the negatives here because we've already figured out the directions for the torques, so we're good. So the magnitude of the charge on the oxygen is 2 times the elementary charge, right? Whereas the charge on the hydrogen is just 1 elementary charge. The mass of the oxygen is 16 atomic mass units. I'm going to label that M0, M sub 0. One atomic mass unit is 1.6725 times 10 to the minus 27 kilograms. And if you can't read that, don't worry about it too much. It's in your textbook, and it's not that crucial to the problem. Pardon me. But the mass of the hydrogen is simply 1 atomic mass unit, or 1 fundamental unit, okay, of mass. Okay. As for the moment arms for each of the 2 torques, as I said, those are not going to be equal because of the center of mass, and therefore the location of the axis of rotation are not going to be equal. Okay. So the moment arms here Okay, so the moment arm for oxygen, that's D sub O, is going to be the distance between them multiplied by the mass of the oxygen over the total mass of the system. Okay, so this is a fraction. So this is 16 over 17, basically. Okay? And whereas the moment arm for hydrogen is D times M sub H over M sub O plus M sub H. This calculation here is simply the calculation for determining the center of mass. Okay, let me. So this is 16 over 17 D, and then D sub H is, I'll rewrite that, MH over MO plus MH, so that's equal to 1 over 17 D. Okay. The nice thing about the recording, even though I moved off screen, you may not have finished writing it all. I'll put it back. But of course, you can always pause the recording and write it at your leisure. Okay. So now we are in a position to calculate things that I want to calculate. First of all, we can get the dipole moments. Okay, the dipole moment for oxygen is simply the charge on oxygen times the moment arm for the oxygen, and that I substitute in the numbers, and that's 32 times E times D over 17. Maybe I should do that in slower motion. Q0 is 2E. D0 is 16 over 17 times D. And so we end up with 32 E over 17, 32 over 17 E times D. How about that? Okay. For hydrogen, it's the charge on hydrogen times the moment arm for hydrogen. And so that's 1E times 1 over 17 D. And so E 1 over 17 times ED. Okay. Now that we have the moment arms, we can start to calculate the torques. The torque on the oxygen is going to be PO times the electric field times the sine of the angle between them, which is 30 degrees. And I'm going to skip a couple of the steps. I'll let you substitute the numbers, check my work. This ends up being 32 ED E sine theta over 17, which when I substitute in the numbers, well, actually I didn't do that. Yeah, so there's that. It turns out when I solved it in here, when I solved it myself, I only substituted numbers at the very end with the total torque. The torque on the hydrogen is PH E sine of theta, which is E times D times the electric field times sine of theta over 17. And so adding those all together, (33 over 17 ED E sine theta). Now I substitute in the given values, and I ended up with 8.46 times 10 to the negative 35 Newton meters. Okay. That is pretty darn exciting. Not so much? Okay. Well, anyway, so what do I want you to really focus on? The definition of the electric dipole moment, which is the charge times the distance of the charge from the center. The total dipole moment of the entire dipole would be PO plus PH. So that would be 33 over 17 ED. That's the total dipole moment, okay? But I can calculate the dipole moment for each charge individually, which is what I did here. Okay, now that I know the numeric value of the torque, I can go and calculate the angular acceleration if I remember the relationship between the torque and the angular acceleration, which of course you do, right? Sure you do. So a torque causes a rotation. To be more specific, a torque causes um, an angular acceleration, which causes a change of angular velocity, which causes a change of rotation. Is caused by a torque. Well, we just calculated the torque. Okay. The relationship specifically is the angular acceleration, which we symbolize with alpha, is the torque that you apply divided by the moment of inertia of in this case, of the dipole. Oh, really? He expects us to remember this? Well, not necessarily. I hope that you have heard of the moment of inertia and that you sort of remember what it's all about. It's effectively the equivalent in rotations to what mass is in straight line motion and translations. Typically, you calculate it, it ends up being, well, it always ends up being something like a mass multiplied by the square of some distance. Here, the moment of inertia is the moment of inertia of the positive charge of the hydrogen plus the moment of inertia of the oxygen. And once again, we have to care about their distances from the axis of rotation. So for the moment of inertia of the hydrogen, that's going to be the mass of the hydrogen multiplied by its moment arm, which we determined already is 1 over 17d, and that's going to be squared. Okay? Meanwhile, for the oxygen, that's going to be the mass of the oxygen times 16 over 17d, and that's also squared. Okay? And so I put that all together, did a little bit of algebra here, and I got, and I'll get out of your way here in a second, 241, check this out, 241 over 17 times the atomic mass unit times d squared. Cool. So what do we have? We solved for the torque earlier. Let me show this to you. Because I like algebra, I'm going to do it algebraically to start with. Okay, so we came up with this expression for the torque. So the torque is equal to this, but the torque is also equal to I alpha. So we have torque is equal to I times alpha. But from part A, okay, here's a good time to calm you down. Do I expect you to be able to do a problem like this on your own without a lot of prompting from me? No. Will I give you a problem like this on the test? No. What's going on here? Why am I wasting your time? I'm not wasting your time. I do expect that you will understand the concepts that I've applied here so that once you understand this problem thoroughly, you'll be able to apply these concepts easily to a much simpler problem that I would give you on a test. Okay? Plus, once in a while, it's fun just to challenge your mind occasionally. Stretch yourself a little bit. Flex your muscles. Classes are coming when you're going to be, a lot more is going to be demanded of you. So the sooner you get some practice in, the better. So, hey, this is science. It ain't English grammar. We're having fun here. Okay, from part A, that was me moralizing. Torque is equal to 33 over 17 ED, electric field sine theta. And so I can equate these the idea here is since the torque is equal to this and the torque is equal to that, since tau is equal to this and tau is equal to that, then these two things must be equal to each other. And so we end up with I just calculated I, that's 241 over 17 m0 d squared. Okay. By the way, this is the fundamental mass, atomic mass unit. This is not the mass of oxygen. The way you can tell that is I'm using a lowercase m, not an uppercase m. Okay. So this is I. Okay. Times alpha is equal to all of this. And a hydroxide is more complicated than a simple dipole. You should expect the solution to be more complicated than a simple dipole. All right. So we're basically done solving for alpha. I did so, and I got 33 over 241 times E, capital E, sine theta over D times m sub 0. Okay, let's see. E is the elementary charge, 1.602 times 10 to the minus 19th coulombs. Capital E is the electric field, 4 times 10 to the minus 6 newtons per coulomb. Theta is the angle between the axis, the orientation of our hydroxide, and the electric field. Theta is 30 degrees. D is the distance between the hydrogen and the oxygen. M naught is the fundamental unit of mass, essentially the mass of a proton. Okay, not quite that, but close enough for our purposes. So we know all of these numbers, and so I plugged in the numbers, and I got 1.93 times 10 to the 11th, positive 11th, 1 over seconds squared. Okay, I encourage you very, very strongly to actually go through the mathematical steps of plugging the numbers in and checking that the units do, in fact, cancel out to be 1 over seconds squared, which, of course, are the units of angular acceleration. So there's that. Fundamentally, the concept of the electric dipole moment and how it's related to the torque on a dipole, or at least a polar object that will cause it to align with the field. Okay, so there's that. And electric fields and electric forces are hard. Isn't there a way to make them easier? Yes, there is. We'll start to talk about that next lecture.